Yeah, so good morning, good afternoon, and good evening to everyone. We're very happy, myself and George Noronha, to welcome you, everyone, to this virtual event. This event does not really come out of a vacuum. It's supposed to be a spiritual continuation of a series of workshops on on relativistic dynamics that, well, started with an event in Mainz in 2016 and continued with the event in Trento in Italy in 2018 and the event in Banff in Canada last year. So, well, I mean, we thought that the virtual technology is a great opportunity to bring together like all the enthusiasm of relativistic dynamics in a low-key event that's supposed to discuss latest developments in the field. Without bringing too much of a carbon footprint, and with actually some ease that is like with a few talks and some generous time for Q&A, etc., etc. So with this, let me thank you on behalf of the organizers for showing up, and let me pass the baton to Jackie, who's going to be the chair in this session.
Thank you. Hold on.
I did it. Oh.
You're muted, Jackie, I think.
Okay, here we go. Now we're fine. So yeah. Just a reminder for everyone, the talks will be 25 minutes. We have plenty of time for discussion after the talk, so please put questions that you may have in the chat or raise your hand after the talk. But I would ask that you keep all the questions afterwards, and we will have a discussion later this afternoon or evening, depending where you are. So if we cannot cover all the questions, we can get to them then. So without further ado, I would like to introduce Gabriel Denicol, and take it away, Gabriel.
Okay, thank you, Jackie, for the introduction, and thank you the organizers, so Michelle and George, for inviting me to this very nice workshop. And I'm looking forward to all the discussion as well and learning about all the new stuff in hydro that you guys have to say. So this talk will be more about the Boltzmann equation, but of course there is a connection to hydrodynamics, and it's done in collaboration with Gabriel Soares, my student, and George Noronha, one of the organizers. So this is just a brief outline of my talk. So I start with a brief motivation from heavy ion physics, then I'll just go discuss a little bit about the Boltzmann equation and this relaxation approximation, which is the issue I want to discuss. So in this talk, I will propose a new relaxation approximation because the previous one has some issues and some problems that must be solved. And I hope this talk will make this clear and show some results that come out of this new approximation. Then I'll end with some summary and perspectives. So this just talk about a little bit about our field in heavy ion physics. So when we talk about relativistic hydrodynamics, of course, one of the main applications is in heavy ion collisions, where we create a hot and dense fluid of QCD matter, which expands very, very fast, very quickly, and cools down. And what people measure at the end of the day are just hadrons and leptons. And of course, this experiment raised a lot of questions about hydrodynamics itself. It's a fluid created in extreme conditions, and one can always ask, if fluid dynamics is applicable in such extreme scenario, and why, and how to formulate, this hydrodynamics in a relativistic setting, which is also a question that comes out, emerges again, every 5 years, and people always coming out with, newer and more interesting answers every time we come back to this problem. This is now my connection to kinetic theory. So when you study the emergence of fluid dynamical behavior, usually kinetic theory is a very nice kind of microscopic approach to investigate this issue, mostly because it's simple enough that you can solve the problem completely. And usually we do that in these kind of Gubser flow and Bjorken flow scenarios. So we consider very highly symmetric cases for which we can solve the Boltzmann equation, usually not even the Boltzmann equation, but this Boltzmann equation with this relaxation approximation. And then we investigate if how a fluid behavior can emerge in this highly symmetrical yet extreme flow configurations, which are very similar to heavy ion collision. So this is a great kind of contribution from our field to the rest of physics, that these very nice solutions come out that allow us to investigate, the emergence of fluid behavior in a very complete way. So here I just show some examples of solutions, Gubser flow, in which you can calculate, for example, the off-equilibrium component of T mu nu and compare to Navier-Stokes theory and Iso-Stewart theory and see how well these two things go in these very complicated Gubser variables. And of course, there's also Bjorken flow, which was solved by Wroblewski, Flokowski, and Strickland many years before, and are also used to investigate all of these issues. Here I just list for the sake of completeness also how kinetic theory is usually applied to heavy ion physics itself. So even we use it even in practice, not only to investigate hydrodynamics, but to investigate to simulate the collisions themselves. So at the very early stages, often we use kinetic theory to describe how the system approaches a fluid state. So for example, this was done more recently by this compost collaboration, in which they try to describe fluid dynamical behavior emerging in a kinetic scenario. It doesn't have to be kinetic theory, but of course, it can be done in kinetic theory, and people try. I mean, if you try to describe photon production or jet quenching or any other thing that requires a microscopic description of the medium, often also kinetic theory is employed here under some approximations. I mean, it's not clear that it is applicable, but it is certainly one of the things that is employed to describe the microscopic state of the medium. And most importantly, I guess, when it comes to the simulations, is just the late stages where you have a hadron resonance gas. And this, pretty much everyone uses a kinetic theory picture to describe the freeze-out procedure and how you convert the fluid picture to a particle picture. And even here as well, this relaxation approximation is often employed to calculate the off-equilibrium corrections to the particle momentum distribution. So kinetic theory is actually very important in studying the emergence of fluid dynamical behavior and also in these fluid dynamical simulations of heavy ion collisions. And it's something that we should always kind of address carefully. Now, this was my brief introduction to the topic. So now I want to discuss actually the Boltzmann equation itself, just show what it is and define this relaxation approximation. So the Boltzmann equation, the fundamental degree of freedom is this momentum distribution of particles, and the Boltzmann equation describes the dynamics of this variable, how it changes due to collisions with this collision term on the right hand side of the equation. Here I just list briefly what is this collision term for if you only consider elastic due to collision. So you have this known expression, integral expression in terms of F, and all the microscopic information is given in terms of this cross section, which describes the probability of this momentum transition in the collision, right? So it's an integral differential equation, and it's usually very difficult to solve, right? Now, when you're interested in the fluid dynamical regime of the Boltzmann equation, one common thing to do is to actually consider the linearized Boltzmann equation around an equilibrium state. So your distribution function, you write it down in terms of an equilibrium distribution plus a correction. In this talk, I call it phi, but of course you could call it any other name. And the equilibrium distribution could be from the Boltzmann exponential to Fermi-Dirac distribution or Bose-Einstein distribution. And then you can approximate the collision term only retaining terms which are linear in phi. And this leads to this linear collision operator and to this approximation to the Boltzmann equation, where now the right-hand side is this linear operator applied to phi. And this is the form of the Boltzmann equation that's usually employed when you derive fluid dynamics from the Boltzmann equation. Usually these terms which are quadratic in phi just produce terms that are kind of neglected in hydrodynamics or just not that important. So most people don't even include them in the codes and so on. The relaxation approximation, at least as far as I understand it, would just be an approximation for this linear collision operator. So even this operator is often complicated enough. We want to simplify it and then just approximate it to a simpler form. Now, before I move on into this issue, I want to discuss about matching conditions. So the moment you linearize a Boltzmann equation around an equilibrium state, you have to define what this equilibrium state is. So what is the temperature, chemical potential, velocities, how these things are properly specified. They, of course, don't appear in the original form of the Boltzmann equation. And the most common way to do this is this Landau and Eckert pictures or matchings, right? So in this case, you usually define the local energy density and particle number or net charge, if in the case, more general case. You consider these things as thermodynamic quantities, and and then you use them to define the temperature and chemical potential and pressure using the thermodynamic relations right down here. Now, this is kind of a common approach to Landau and Eckert. So this is done in the same way in both pictures. And the velocity is defined either by following the flow of energy, like on the left-hand side, or the flow of net charge or particles on the right-hand side. And of course, you could do this in any other way, right? And nowadays, people are proposing more and more approaches to this. In particular, even changing the part above of how defining temperature and chemical potential, which usually we never really touched, but now it's being discussed more deeply. In kinetic theory, these things just appear as constraints in the integrals of phi. So in the Landau picture, these two integrals involving phi, the non-equilibrium correction must be 0. And the Eckert picture, these two integrals must be 0. The main difference being the second one, which either has a factor of energy or not, right? So this kind of this condition on phi fixes the velocity and temperature and chemical potential of your equilibrium state. One of the advantages in kinetic theory is that actually you can even consider more general matching conditions. You can do anything you want. So you can consider, for example, these matching conditions I list here with arbitrary powers of energy in these integrals of phi, and which leads to, let's say, any matching condition you want. I don't know if you can do that outside of kinetic theory, but in kinetic theory, you are really open to studying these matching procedures very well. And I will do that in this talk.
In the last equation, z is a power, or is it the z direction?
No, it's a power, Uli. Thank you. It's a power. And of course, it doesn't have to be powers of anything. You can do these matching conditions with any function of energy that you want. As long as they are linearly independent, you're fine. You will be able to define temperature and chemical potential in a proper way. Now, I guess the main part to understand this talk is that this linear collision operator has two fundamental properties. First of all, quantities which are conserved in the collision, like 1 in the case of binary collisions and energy momentum, the form momentum of your particles, they are eigenvectors of your linear collision term with 0 eigenvalue. And this is a consequence of of conservation laws. And also, if you like to, you can also define this collision operator to be a Hermitian operator, which is just defined by this property here. And if you combine these two properties, you get the conservation laws, right? You get that the first and second moments of the Boltzmann equation will give you the two conservation laws that you expect. In our case, particle number conservation, because we consider only elastic collisions, and energy momentum conservation. These are just consequences of these basic fundamental properties of the linear collision operator. Now, what I will show now, I will discuss this relaxation approximation, and what I will show you is that essentially the usual RTA approximation does not respect these properties of the collision operator, and they do not lead to conservation laws in general. And that's the issue that I will try to solve in this talk. So this relaxation approximation, as I said, is a simplification of the collision operator, of the linear collision operator, this L that I defined. And it just describes some exponential relaxation to equilibrium. The first time I know of this approximation in relativistic system is by Marle. So he tried to approximate it, the linear collision operator in this form right here. It's proportional to non-equilibrium correction, but he added this mass term, which made it very difficult to apply this to ultra-relativistic systems. And then very quickly, Anderson and Whiting corrected this approximation and defined it in a different form. So they instead of putting the mass there, they put this kind of energy in the local rest frame of the system times the non-equilibrium correction here. And they showed that this kind of form was able to recover basic results from Grad's theory, like transport coefficients and so on. And this is the kind of form of approximation that we use to this day, right? Many papers solving the Boltzmann equation in our field use this approximation of the linear collision operator. And in this case, this relaxation time is the kind of where all the microscopic information is kind of inserted, right? And it could be a general function of energy or even temperature, if you want. And as I said, the problem is that both these models do not satisfy the basic properties of the collision operator that I showed in the previous slide, in the set of conservation laws. You can show this rather simply. So if you take the Anderson and Whiting approximation of the collision term that we use quite often, just this right up here in the slide, and you calculate the first and second moment of the Boltzmann equation, you don't get 0, you get these integrals of phi that I show right here. So particle number and energy momentum are in principle not really conserved, and the conservation laws are not satisfied. Now, why is it not a great problem to us? Is that usually these integrals will vanish for a different reason. Is that if you consider constant relaxation times, and here by constant I mean no energy dependence, they can still depend on temperature, and you also use the Landau matching, then these integrals will vanish because of the Landau matching procedure. And then you get the conservation laws as you should. But if the relaxation times are not constant, or you don't use the Landau matching procedure, then the conservation laws will not really work. Now, of course, you could always make this work simply by choosing matching conditions such a way that this is 0, and then your matching condition will always be fixed by this problem, by enforcing the conservation laws. But at least I believe this is not an elegant solution, that this conservation law should really come from the operator itself, from the approximation itself, and not from enforcing matching conditions. And also the other issue is that nowadays we have this theory by Benfica, Disconzi, and George, in which they show that other matching conditions are actually required. And so I guess nowadays other matching conditions is something that you really want to explore. And in this sense, this old or usual traditional approximation maybe is not good enough to study things like this, the fluid behavior of this theory from kinetic theory, from the Boltzmann equation. Okay, so the solution, how do you solve this, right? The solution is rather simple. It's even textbook simple. It is known, I mean, at least in the non-relativistic case, people do this rather often. And the problem you can think in Hilbert space is that the usual approximation by Marley and Anderson-Whitting is just saying that the collision operator is just the identity operator. And then, of course, this will never have eigenvalues which have eigenvectors which have a 0 eigenvalue, right? I mean, it just won't work. So our solution to this is to propose, instead of saying that the linear collision operator is proportional to the identity operator, we propose this kind of a projection operator, where these lambdas are the eigenvectors with 0 eigenvalues of L. And here we just assume it's an orthonormal basis, so they just have just unitary. And obviously this kind of approximation here will always satisfy that these lambda n's will be eigenvectors with 0 eigenvalue. So that's kind of what we propose. This is the main part of the talk, even, that instead of going with Anderson-Whitting and Mao, which just have this identity operator, they just change the factors, right, that multiply the identity, we go with this projection operator, just to ensure the conservation laws are always applicable. This is even an exercise in this book by Reichel. So there's the book Modern Course in Statistical Mechanics, and problem 11.7 is exactly her telling the students how to correct how to approximate the collision operator in such a way that these basic properties are satisfied. Now, how does this look like in the usual, like a usual notation outside of Hilbert space? So if you just write the expression I just showed you in the conventional language, this is what the approximation looks like. So this is the kind of prefactor of energy over relaxation time times F0 that usually appears. You have the usual term, which is just a non-equilibrium correction phi, and all these terms here are just the counter terms that ensure the conservation laws are always valid, right? These brackets just constitute this kind of integrals with this measure here, with the relaxation time.
Remind us what capital P is, P1?
Yeah, so, and these capital P's are just orthogonal polynomials, which are orthogonal relative to this measure here, to this how do you say, internal product. So they're just powers of energy. So P0 is just 1. So when I put this 1 here, it's just P0, and P1 is just a linear function of energy in such a way that this integral, this orthogonality relation is satisfied. So I won't really list them here, Uli, but I just display the general properties. They can usually be easily calculated. If tau r is simple enough, this will be some sort of Laguerre polynomials usually in the classical limit. So this is our approximation. In this case, we still have an integral differential equation for phi, because now these brackets involve integrals of phi. So it's a little bit more complicated than the old approximation, but still considerably simpler than the full linear collision operator in the Boltzmann equation. So now what I will do for the remainder of this talk is just show you solutions of this phi to first order in the graded expansion, this Chapman-Ensor expansion. And in particular, I will show how the matching will affect the solution of phi, because now we can actually study this problem rather carefully. So now I'll just discuss this hydrodynamic limit of the equation using this first order Chapman-Ensor approximation, which I don't explain it very well here, but I just list the answer. So if you go to first order in gradients and you want to find this phi, it just satisfies this equation right here. With the left-hand side is just derivatives of the equilibrium distribution, and the right-hand side is just an integral equation involving phi that you have to invert, but it's not that difficult to invert, right? And to first order, the derivatives of F0 just involve just gradients of this theta is the expansion rate, it's just d mu u mu, the four derivative divergence of the velocity. Here we have gradients of chemical potential, and here we have the shear tensor, which is just a derivative of velocity that appears in Navier-Stokes theory. So if we invert this equation here, the general solution for phi has this form here, and you just have to specify these functions fp 0, 1, and 2. And this form here is exactly the same form you would get in the old RTA approximation. So this general solution is just not really affected by changing the linearized form of the collision term. It will still be the same solution even for the full collision term. But now the energy dependence will change. In particular for the scalar and the vector terms. For the tensor, it doesn't matter. So the shear viscosity and the shear and pi mu are not affected by any of this. Only the heat flow and the bulk will be affected by this approximation. So the shear term, this is the solution for F2, is just 1 over temperature tau r over energy. Same as before, as I said, not affected by anything. But here, let me show you the solution for the vector term, this F1. So there's a lot of notation hidden here, so you don't have to understand most of it. All I want you to know is that this first term here is the usual solution. So this is what you get if you use the usual RTA approximation. And this is even used in many papers where you calculate delta F for in heavy-ion collisions for terms including heat flow. And all the terms on the right-hand side, on the second term, are new, and they are due to this new correction term to enforce the conservation laws. And you even see here that depends on the choice of matching condition. So if I choose this matching condition here with an arbitrary power of energy, which here Z is this power, you see that this matching choice appears in F, right? So, and this of course will also affect your transport coefficients. If you calculate them, they will depend on matching as well, right? So, and now this is something that we can at least calculate in this RTA approximation that we just described. So here is just 2 examples of this energy dependence. So if I put the relaxation time here as some power of energy, which could be 0, which just means that constant relaxation time, this is the plot above, and below is just gamma equal 2, just a quadratic dependence on energy, just a choice. And here we show you several choices of matching procedures. So this L values of Z are just the powers of energy that we insert there. And L equal 2 will be the shear solution, which is just not affected by any of the matching choices. And the other curves are the vector solutions, which could be affected. So you see that for gamma equal 0, they're not that much affected by the matching choice, but for gamma equal 2, for another choice of the energy dependence of the relaxation time, you have a dramatic effect on the energy dependence due to matching here. The same thing occurs for the scalar contribution, this function F0, which multiplies the expansion rate. So again, the first term, which is already complicated enough, it's down here, is what you get usually just in the Anderson-Whitting approximation of the linear collision term, and everything else is a new term that you get by enforcing the conservation laws. And again, here you see these factors, these powers of R and S, which are corrections due to the matching condition. So if you consider like a general matching condition where you have a power of R, the energy to the power of R and energy to the power of S here, and you enforce this interval to be 0, this will affect all the other corrections to the remaining terms of the energy dependence of F, right? So here again, I show you some plots of this energy dependence of the distribution function, again for gamma equals 0 and 2. So the plot above is for a constant relaxation time, and the plot below is for a quadratic dependence in the relaxation time, and they're all functions of energy. So again, here we see that, for example, this is fixing r equal 1. So one of the integrals is just the usual Landau procedure, and then we change s to be either 0, 2, 3, and 4. It cannot be 1. You cannot choose the same power for r and s. Otherwise, you don't get two matching conditions, just get one. And again, here we see a strong dependence of this energy dependence on your choice of matching in both scenarios, like for either for a constant relaxation time or for a quadratic energy dependence. We see that it does depend on your choice of matching. And in this case here, it's also rather obvious. It depends on tau r itself, right? Gamma equals 0 and gamma equals 2 are very different, provide very different energy dependencies for your distribution function. So given that, I want to finish this talk. I think I still have 1 minute. I'll just go through very quickly to my last slides, but just show you results for the transport coefficients. The shear viscosity I won't really show you because it's not affected. Actually, I will show you because I will investigate the energy dependence, but the shear viscosity won't really be affected by the approximation itself. It will be the same answer as the usual Anderson-Whitting approximation, but the bulk viscosity and the heat flow will be affected by many of this. So now this is the shear viscosity and how it changes with relaxation time. So if you consider constant relaxation time or you start changing energy dependence, this is how your shear viscosity over normalized by this factor here changes with mass. So this zeta is mass over temperature. I forgot to put here. But now we can also calculate properly how the heat flow changes, right? Before, if you use the usual Anderson-Whitting approximation, you only get the right answer for gamma equals 0, a constant relaxation time. You wouldn't be able to change this energy dependence, but now we can do that. And we can check how this transport coefficient changes with the energy dependence of the relaxation time. And you see that there is indeed a large dependence here as a function of mass over temperature.
So Gabriel,
and finally,
unfortunately, we're out of time.
This is
just flash
my
the
last slide here. Okay. Yeah. So this is just the bulk result. You can just look very briefly here or look later. And this is my conclusion slide, which I'll just leave it here for you guys since I'm over time. So thank you for your attention, and I'm open for questions now.
All right, thank you very much, Gabriel, for the nice talk. So just to remind speakers, I would like you to either put your question in the chat or raise your hand. And I do notice that apparently with your new relaxation time and method going beyond that, you go from scalar to escalar. So I thought that was quite interesting.
That's the Portuguese, the Brazilian in me.
Yeah, I know.
Thank you.
Yeah. So, okay. Jan Fotakis has a question. Jan, do you want to unmute yourself or do you want me to just read it?
I can just ask it. So can you hear me okay?
Yes.
So, hey, Gabriel, a very nice talk. Thank you so much. I was just wondering, you were talking a lot about different choices of the matching conditions, and usually these historically introduced matching conditions have a physical interpretation, such that, for example, off equilibrium contributions to the energy density or the number density vanish, and that the state is matched to a thermal local equilibrium state. So which would fix the orders in your choice of the matching conditions, right? So could you maybe explain why you discussed different matching conditions, different choices, and what they would mean? Like, can you elaborate a bit more about that?
Well, I think the main motivation is, so of course, as I said, to me as well, the Landau matching condition is the most simple one to understand, right? That you say that essentially that your temperature and chemical potential describe your full energy and particle density of your system. But of course, that does not have to be the case. You could, in principle, have just part of your energy density thermal, and there's a non-equilibrium correction there. That's also possible. It's more complicated, but it's also possible. And I think the main physical reason to consider that is what George and his collaborators showed a few years, maybe two. Yeah, now I guess it's still recently, right? I mean, we can still say recently that if he formulated a new version of Navier-Stokes theory in which he considered also space-like gradients in the derivation of the theory. And in that specific case, he showed that this theory is only causal if you're not in Landau or Eckert matching conditions. So his new theory kind of motivates you to go beyond the standard Landau and Eckert pictures, because for these two pictures, his approach simply does not work, right? And so that's to me one of the reasons. How to properly define these matching conditions beyond kinetic theory, I don't know, because kinetic theory is very easy, right? As I showed here, you can just define them in terms of these integrals of phi, and you can do many choices of matching conditions. But one thing that is clear here is that these new matching conditions, they involve things which are beyond T mu and N mu, right? So you somehow need additional variables which are not the usual conserved currents to specify these these matching conditions. In kinetic theory, you have them. You just have other moments of F that you can use.
Yeah.
In general, I don't really know.
Thank you.
I don't know how to raise my hand. Somehow this interface is different from other days. Can I just ask a question?
Yeah, go ahead, Uli.
The last two slides that you showed seem to me to indicate that when you deviate from the standard matching conditions, you pay a price because the transport coefficients increase, and therefore I assume the dissipative flows will also increase.
Oh, here, sorry, Uli, I went too quickly over these slides, right? So these are for the traditional matching conditions, just changing the relaxation time. So this is for Landau matching condition here. We're just checking how the energy dependence of the relaxation time affects these guys. I also have plots for these coefficients changing the matching conditions, but then I decided not to show them here because when we change the matching condition, we also increase dramatically the number of transfer coefficients because we have this.
I misunderstood then. So if you compare your improved linearized collision term with the original one, where do you see the biggest difference, and what does it mean in practice?
Well, it depends how you compare. So for example, if gamma is 0, so this black curve is just the same as usual. We get the same answer as the other. The thing is, if I want to compare my results with the usual one, I would have to take the usual result and calculate it in the wrong scenario where there are no conservation laws. Of course, I could do that, but I don't know if it's useful.
And so that means if you take the usual scenario, in that limit, the projection just does the same thing as imposing the matching condition that you can conserve. So in that case, the way you conserve, you impose the conservation laws is exactly the same. It's just mathematically in a different, you take care of it already on the level of the collision operator rather than separately.
Yeah, because I mean, so let's say in the old approach, if you want to change your energy dependence of your relaxation time, the only way to be consistent with conservation laws is if you adopt a new matching, right? And I don't even know if people were doing that, to be honest, right? I mean, I guess most people didn't realize this was an issue. So essentially, here we can just do these things freely, right? Whatever our choice of relaxation time or matching, the conservation laws will be respected, right? And so we can actually move in all these dimensions. We can change this gamma factor that I put up here, or we can change the matching conditions and investigate how transport coefficients and the distribution function changes with those guys rather freely. While in the other approximation, you simply just cannot do that, right? So a plot like this will not be possible in the usual Anderson-Whiting equation, because for each of these curves, you'd have to have a different matching condition to get the conservation law right. So it's very hard to compare, actually, this approximation with the old one in a consistent way, let's say like that.
Thanks.
Are there other questions? I think I could have one more, otherwise I'll probably then move on.
In fact, I do have another question, but let other people go first.
Okay, may I have one question? I don't know how to raise my hand.
Yeah, that's actually another thing. You can't raise the hand.
Okay.
In the future, please write a question in the chat. Sorry about that. But go ahead.
A very nice talk indeed. So my question is like that, we can understand that if we have a momentum dependent relaxation time, we cannot have the conventional Landau matching. And so that is why we have to have some extended Landau matching. But the problem is that with Landau matching, the previous case, the Landau matched energy density or velocity are defined as the equilibrium energy density or velocity. When this additional part of Landau matching is taken into consideration, so we have some additional part in energy density or velocity in the expression of T mu nu. Then it raises a questions about what is the definition of equilibrium temperature and velocity. That is my confusion, because with this extended Landau matching things, both energy density and velocity picks up additional pieces which are function of shear pi mu nu or bulk pi or this diffusion flow, etc., etc. Then a question appears: what is my definition of temperature for the system? Because the definition of energy density extracted from u mu u nu T mu nu is picking up not only epsilon plus pi, or in second order pi mu nu pi mu nu. So that raises the definition of equilibrium temperature. So that is what I would like to ask: how to define the equilibrium temperature? What is the definition of temperature in such situation?
So I mean, at least in the way I see it is the following way. So the question is, temperature will always be defined following this kind of blue box here in the middle, right? But the question is, what is the n and epsilon that you put here? Yes. So in the Landau and Eckert case, you just put the full local energy density and the full net charge to define this equilibrium entropy, and then everything comes out, right? But in other matching procedures, you have to divide essentially your energy density into an epsilon plus a delta epsilon.
Exactly, that delta part, which contains the pi mu nu thing. So what is the definition of T now?
No. In principle, it is a new variable, right? I mean, but there will be a pi mu nu as before, and there is a delta epsilon now, which is this off equilibrium component of your energy density. And how to define that in general, I don't really know. In kinetic theory, you define that by these integrals. That these integrals here fully specify this delta epsilon in principle, right?
Okay.
But only in kinetic theory I know how to explain this to you. In general, you need variables which are not hydrodynamical, right?
Because our definition of energy density is u mu u nu T mu nu. Now T mu nu is picking up one additional part, let's say delta epsilon u mu u nu. So contracting that thing, our energy density, equilibrium energy density is something like epsilon plus delta epsilon, and the delta epsilon is function of pi or pi mu a second order shear or something like that. So now appears how to define the question appears how to define the equilibrium temperature or equilibrium velocity, because it's like that they should also carry some additional part contributed by this shear and bulk or heat flow. So that is what confusing me.
So I think we should move this discussion to the discussion afterwards in the afternoon, since we do have 40 minutes. And I know Uli also had a question then, but I think we should move to the discussion afterwards. Just because we started a little bit late, we should continue on so people can remain on schedule. So let's thank Gabriel once again. It was for the very nice talk. And let's move on. Yes,